Welcome to the Nocturnal Astronomer. I'm Atlas Reid, your guide through the cosmic mysteries that unfold in our night sky. Tonight, we turn our attention to one of November's most distinctive celestial events, the Taurids meteor shower. Unlike the swift streaks of summer meteors that flash across the sky in an instant, the Taurids move with deliberate grace, bright embers drifting through the darkness. These are not ordinary shooting stars. They are the remnants of an ancient comet, fragments that have been orbiting the sun for thousands of years, waiting for their moment to ignite in Earth's atmosphere. Over the next hour, we will explore the fascinating story of these meteors. We will journey back 10,000 years to understand where they came from, examine the peculiar comet that gave them birth, and discover why they produce some of the brightest fireballs visible from Earth. We will also look at the two streams that make up this shower, the southern and northern Taurids, and understand why November becomes the stage for their annual display. If you enjoy these explorations of our cosmic neighborhood, please consider giving this video a thumbs up and subscribing to the channel. And here is something fun. After watching, leave a comment telling me which constellation you find easiest to spot in your night sky. I am always curious to hear what captures your attention on clear nights. Now then, let us dive in. The story of the Taurids begins not thousands but tens of thousands of years ago, in an era when humans were still painting on cave walls. At that time, somewhere in the dark reaches of our solar system, a massive comet measured approximately 40 kilometers across. To put that in perspective, imagine a celestial iceberg larger than many of Earth's major cities. This giant wanderer, composed of ice, rock, and frozen gases, traced its path around the sun in a repeating orbit that brought it periodically through the inner solar system. Then, somewhere between 10,000 and 30,000 years ago, something catastrophic occurred. The exact cause remains a subject of scientific study, but the result was unmistakable. The giant comet broke apart. Perhaps it came too close to a large planet, and gravitational forces tore it to pieces. Perhaps internal pressures from sublimating ice caused it to fracture from within. Or possibly it collided with another body in space. Whatever the mechanism, the breakup was thorough. What had been a single massive object became a collection of smaller bodies, each inheriting a similar orbit around the sun, each carrying with it a trail of debris, dust, and pebbles. Today we call this family of fragments the Encke complex, named after the most prominent surviving member. This complex is not just one or two pieces. It includes the comet known as Encke, several asteroids, and multiple meteor streams that Earth encounters at different times of the year. Think of it like a river that is broken into many smaller streams, all flowing in roughly the same direction but spread across a wide area. When Earth crosses these streams, we see meteors. The Taurids visible in November are just one manifestation of this ancient destruction. The scale of this debris field is staggering. Scientists have determined that the Taurid meteoroid stream is the largest in the inner solar system. Because the material has spread out over thousands of years, Earth takes several weeks to pass through it completely. This extended duration is why the Taurids do not have a sharp peak like many other meteor showers. Instead, they produce a steady trickle of meteors throughout late September, October, and November, with activity gradually rising and falling rather than spiking dramatically on a single night. Understanding this origin story helps us appreciate what we see when we watch for Taurids. These are not random particles of dust. They are pieces of history, fragments of an object that existed before human civilization began. Each meteor that burns in our atmosphere represents a tiny piece of that ancient comet, completing a journey that began when the breakup scattered material across millions of kilometers of space. The light we see is the final chapter of a story written in the distant past, connecting us to events that unfolded when mammoths still walked the Earth. At the heart of the Taurid mystery is Comet Encke. This comet holds several remarkable distinctions. It possesses the shortest orbital period of any reasonably bright comet known to science, taking just 3.3 years to complete one orbit around the Sun. To understand how unusual this is, consider that Halley's Comet, perhaps the most famous comet of all, takes 75 to 76 years to orbit. Encke makes the journey in less than 5% of that time. The comet's naming itself is unusual. Most comets are named after their discoverers, but Encke breaks this pattern. The first observation was made by French astronomer Pierre Méchain on January 17, 1786. Caroline Herschel, the renowned British astronomer, spotted it independently in November of 1795. Then French observer Jean-Louis Pons found it yet again in October 1805, along with two other astronomers on the same morning. For years, no one realized these were all sightings of the same object returning periodically. It was German mathematician Johann Franz Encke who, through laborious calculations in 1819, connected these observations and recognized them as the same comet returning every few years. He calculated its orbit with such precision that he correctly predicted its return in 1822. The comet was subsequently named in his honor, though Encke himself always modestly referred to it as Pons' Comet, insisting he had merely calculated what others had discovered. The physical characteristics of Comet Encke reveal why it behaves so distinctively. Its nucleus measures approximately 4.8 kilometers in diameter. That makes it relatively small compared to some comets, roughly the size of a large mountain. The comet orbits at a low inclination of just under 12 degrees from the plane of Earth's orbit, which partly explains why Earth encounters its debris so regularly. Its orbit brings it no farther out than Jupiter's path, unlike most comets that venture to the outer solar system or beyond. Perhaps most intriguingly, Encke is what astronomers call a worn-out comet. After countless thousands of passages near the Sun, much of its original ice has sublimated away. This is why Encke rarely develops much of a visible tail, unlike the spectacular-tailed comets we occasionally see. Think of it like a bar of soap that has been used over and over. The basic structure remains, but most of the original material has gradually worn away. What is left is likely a fairly compact core of silicate rock, thinly mixed with remnants of ice. Encke also exhibits another fascinating behavior. Its orbital period decreases slightly with each return, shortening by about 2.5 hours per orbit. For decades, this puzzled astronomers. Eventually, scientist Fred Whipple explained it in 1950. As the comet heats up near the Sun, jets of gas escape from its surface. These jets act like tiny rocket engines, pushing against the comet and gradually altering its orbit. This jet effect, combined with the comet's rotation, causes the steady orbital decay astronomers have measured for over 2 centuries. The Taurids are not a single meteor shower, but rather 2 distinct streams that Earth encounters sequentially in autumn. The southern Taurids arrive first, becoming active around September 20th and continuing through November 20th, with their predicted peak around November 5th. Shortly after, the northern Taurids begin, active from approximately October 20th through December 10th, with a peak near November 12th. During late October and early November, both streams are active simultaneously, creating an overlap period when observers might see meteors from either stream. This division into 2 branches stems from gravitational perturbations, primarily from Jupiter. Over thousands of years, Jupiter's immense gravity has pulled and tugged on different parts of the debris field, stretching it into distinct regions. Picture a cloud of dust and pebbles slowly being stirred by an invisible giant hand. Some material drifts one way, some another. Eventually, what was once a unified stream becomes two streams occupying slightly different paths through space. When Earth crosses the first path, we see southern Taurids. When we cross the second path a bit later, we see northern Taurids. The parent bodies of these two streams differ slightly. The southern Taurids originate directly from Comet Encke itself, the material shed as the comet travels its orbit. The northern Taurids, however, trace their origin to asteroid 2004 TG10. This asteroid was discovered by the Spacewatch program in October 2004. Scientists quickly recognized that its orbit closely matches that of Comet Encke. The most widely accepted explanation is that this asteroid is itself a large fragment that broke off from Encke, a child of the original breakup, a chunk large enough to survive as a distinct body rather than disintegrating completely. Despite their slightly different origins, both Taurid streams share common characteristics. Both produce about 5 meteors per hour under ideal dark sky conditions during their peaks. This rate is modest compared to major showers like the Perseids or Geminids, which can produce dozens of meteors per hour. However, what the Taurids lack in quantity, they compensate for in quality. Both streams are rich in fireballs, exceptionally bright meteors that can equal or exceed the brightness of Venus in the night sky. The radiant point, the location in the sky from which the meteors appear to emanate, is the same for both streams, located in the constellation Taurus. This makes sense given their common ancestry. However, the slightly different angles at which Earth encounters each stream mean that careful observers can sometimes distinguish northern Taurids from southern Taurids based on subtle differences in their trajectories. For most casual observers, though, the distinction is academic. What matters is that November offers an extended window to see these distinctive slow-moving meteors, with both streams contributing to the overall display throughout the month. The overlap period in early November creates the best viewing opportunity. During these nights, meteors from both streams can appear, effectively doubling the rate compared to times when only one stream is active. This is why many astronomy guides highlight early November as the optimal time for Taurid watching, even though neither stream has a particularly dramatic peak. Within the broader Taurid stream exists a denser concentration of material that astronomers call the Taurid swarm. This is not a constant feature, but rather a region of thicker debris that Earth encounters only during certain years. Think of the Taurid stream as a river of particles flowing around the sun. Most of the time, the river is shallow and spread out. But in some sections, there are deeper pools where debris has concentrated. When Earth passes through these pools, meteor activity increases noticeably, and the frequency of bright fireballs rises dramatically. The swarm follows a cycle of approximately 7 years, though the exact period is somewhat variable. During swarm years, observers may see 2 to 3 times more Taurids than during regular years, with a particularly noticeable increase in fireballs. Those meteors bright enough to cast shadows and occasionally fragment spectacularly in the atmosphere. The next significant swarm encounter is predicted for 2022 through 2025, with peak activity expected around 2025. However, predictions about the swarm remain imprecise because the exact distribution of material in the stream is not perfectly mapped. What makes the swarm particularly interesting to scientists is not just the increased meteor counts, but what it reveals about the structure of the debris field. The swarm likely represents material that has not spread out as much as the rest of the stream, possibly because it was ejected from the parent comet more recently or because gravitational resonances with Jupiter have kept it more concentrated. Some researchers have proposed that the swarm might contain larger fragments, which would explain the abundance of bright fireballs during swarm years. Historical observations support the existence of the swarm cycle. Astronomers have noticed periodic increases in Taurid activity roughly every 7 years, going back decades. The years 1955, 1981, 1988, 2005, and 2015 all showed enhanced Taurid activity. These observations have allowed researchers to refine their understanding of when Earth is most likely to encounter the denser regions of the stream. The size distribution of particles in the Taurid stream differs from many other meteor showers. While most showers consist primarily of tiny dust grains, the Taurids include a higher proportion of pebble-sized and even larger fragments. This is why Taurid meteors tend to penetrate deeper into the atmosphere before burning up, creating those characteristically slow, long-lasting trails. During swarm years, the number of these larger fragments increases, leading to more frequent bright meteors. Understanding the swarm has practical implications beyond astronomy. Larger meteoroids pose potential hazards to satellites and spacecraft. By studying when Earth encounters denser regions of the Taurid stream, scientists can better assess periods of elevated risk. Additionally, the swarm provides clues about how debris from cometary breakups evolves over time, information relevant to understanding other meteor streams and the long-term fate of cometary material in the inner solar system. The Taurid swarm is thus both a beautiful celestial phenomenon and a natural laboratory for planetary science. The defining characteristic of Taurid meteors is their remarkable slowness. While most meteors streak across the sky at speeds between 30 and 70 kilometers per second, Taurids travel at a leisurely 27 kilometers per second. This might still sound fast, and it is, but in astronomical terms it makes Taurids among the slowest meteors visible from Earth. To put this in perspective, if a typical Perseid meteor takes 1 second to cross a patch of sky, a Taurid might take 2 or even 3 seconds to cover the same distance. This slow speed results directly from the geometry of their orbit. Meteor speed depends on the relative velocity between Earth and the meteoroid. When a meteor stream approaches Earth head-on, the speeds add together, producing very fast meteors. But the Taurids approach from behind, overtaking Earth in its orbit. Think of 2 cars on a highway. If they are traveling in the same direction and one overtakes the other, their relative speed is just the difference between their speeds. That is essentially what happens with the Taurids. Earth and the meteoroids are both moving around the Sun in the same general direction, so their relative velocity is lower. The slow speed has important consequences for what we see. When a meteoroid enters Earth's atmosphere, friction with air molecules heats it to incandescence. The slower the meteoroid travels, the longer it remains visible before completely ablating. This is why Taurid meteors often appear as long, graceful streaks rather than quick flashes. Some Taurids remain visible for 3 to 5 seconds, an eternity compared to faster meteors that vanish in a fraction of a second. The slow speed also contributes to the frequency of Taurid fireballs. A fireball is defined as a meteor brighter than magnitude -4, roughly the brightness of Venus. For a meteor to become that bright, it typically needs to be relatively large and penetrate fairly deep into the atmosphere. Fast meteors burn up quickly at high altitudes. Slow meteors, by contrast, can penetrate deeper before ablating completely. This gives larger Taurid meteoroids more time to heat up and glow brilliantly. The colors of Taurid meteors provide clues about their composition. Many Taurids appear orange or yellow, sometimes with hints of green. These colors arise from the emission spectra of vaporized elements. Orange and yellow typically indicate sodium, a common element in cometary material. Green suggests the presence of nickel or magnesium. The specific mix of colors in a Taurid meteor reflects the chemical composition of that particular fragment of Comet Encke. Occasionally, a particularly large Taurid will fragment during its passage through the atmosphere, breaking into multiple pieces that create a spectacular display. These fragmenting fireballs can leave persistent trains, glowing trails of ionized gas that remain visible for several seconds after the meteor itself has vanished. The slow speed of Taurids makes these fragmentation events especially dramatic, as observers have time to watch the meteor break apart and see each fragment follow its own trajectory before burning up. To observe the Taurids, you first need to locate the constellation Taurus in the night sky. During November, Taurus rises in the east during early evening and climbs steadily higher as night progresses, reaching its highest point around midnight. The constellation is one of the easier patterns to identify, thanks to several distinctive features that serve as landmarks for navigation. The most recognizable feature of Taurus is the Pleiades, also known as the Seven Sisters. This tight cluster of stars appears as a tiny dipper-shaped group to the naked eye. Through binoculars, dozens of stars become visible, creating a jewel box effect. The Pleiades sits on the shoulder of the celestial bull. Once you have found this cluster, you have found the general region of Taurus. The second major landmark is Aldebaran, the brightest star in Taurus. This orange giant marks the eye of the bull and glows with a distinctive reddish hue. Aldebaran has an apparent magnitude of about 0.85, making it easily visible even from light-polluted areas. It sits within a V-shaped pattern of stars called the Hyades, an open cluster that forms the face of the bull. The Hyades is one of the nearest star clusters to Earth, located about 153 light-years away. The radiant point of the Taurids, the spot from which meteors appear to emanate, is located near the Hyades cluster, close to Aldebaran. However, here is an important point about observing meteor showers. You should not stare directly at the radiant. Meteors can appear anywhere in the sky, and those appearing closer to the radiant will have shorter trails because you are seeing them more head-on. The most spectacular Taurids often appear 30 to 60 degrees away from the radiant, where their long trails are most evident. For optimal Taurid viewing, choose a night during early November when the moon is not too bright. The moon's phase significantly affects meteor visibility. During a full moon, the sky is so bright that only the very brightest meteors are visible. A new moon or crescent moon provides the darkest skies and the best conditions for seeing fainter meteors. Check a lunar calendar before planning your observation session. Location matters as much as timing. Get as far from city lights as possible. Light pollution washes out fainter meteors, and with the Taurids producing only 5 to 10 meteors per hour even at peak, you want to see every one. Drive to a dark site where you can see the Milky Way clearly. Give your eyes at least 20 minutes to adapt to the darkness. Avoid looking at your phone or any bright lights during this adaptation period, as even brief exposure to bright light will reset your night vision. Dress warmly. November nights can be quite cold, and you will be sitting or lying still for extended periods. Bring a reclining chair or blanket so you can comfortably look up without straining your neck. Point yourself generally toward the southeast, where Taurus will be well placed during late evening hours, but let your gaze roam across the entire sky. The Taurids offer more than just a beautiful display. They serve as an important tool for scientific research. By studying the Taurids, astronomers gain insights into the composition and evolution of cometary material, the dynamics of meteor streams, and the history of our solar system. Each Taurid meteor that burns in our atmosphere is a sample delivered free from space, providing data about material that formed in the early solar system billions of years ago. One area of active research involves the potential hazard posed by larger fragments in the Taurid stream. While most Taurids are harmless pebbles that burn up completely in the atmosphere, the stream undoubtedly contains larger rocks and possibly even small asteroids. Asteroid 2004 TG10, the parent body of the northern Taurids, is just one known example. Statistical analyses suggest other large fragments likely exist within the stream, some potentially large enough to survive atmospheric passage and reach the ground as meteorites. Some researchers have proposed that impacts from large Taurid fragments may have influenced human history. The Younger Dryas impact hypothesis suggests that approximately 12,800 years ago, fragments from the Taurid stream may have struck Earth, causing widespread fires and climate disruption. This hypothesis remains controversial, with evidence both supporting and contradicting it. What is clear is that the Taurid stream contains material large enough to cause significant damage if it struck Earth, making continued study of the stream important for planetary defense. The study of meteors also helps astronomers understand how material is distributed throughout the solar system. Meteor streams like the Taurids show how debris from a single parent body can spread over vast distances and how gravitational interactions with planets gradually disperse and reshape these streams over thousands of years. The Taurids, being one of the oldest and most dispersed meteor streams we encounter, provide an excellent case study of these long-term dynamical processes. Looking ahead, we can expect to continue seeing the Taurids every November for thousands of years to come. The stream will gradually continue to spread and disperse, possibly becoming even more diffuse over time. Future encounters with the swarm, particularly around 2025, offer opportunities for detailed study with modern instruments. Professional astronomers will use radar, cameras, and spectroscopic equipment to gather data on meteor composition, velocity distribution, and the three-dimensional structure of the stream. For amateur astronomers and casual skywatchers, the Taurids represent an accessible and rewarding target. Unlike some meteor showers that require staying up until the pre-dawn hours, the Taurids are well placed during comfortable evening hours. Their slow speed makes them easier to spot and enjoy compared to the quick flashes of faster meteors. And the possibility of seeing a brilliant fireball adds excitement to any observing session. Each November, when Taurus rises in the east and Earth plunges through the ancient debris of Comet Encke, we are reminded of our connection to the larger cosmos and the dynamic processes that have shaped our solar system since its formation. And on that note, we conclude our exploration of the Taurids, November's slow-moving celestial wanderers. We have traced their origins back to a giant comet that shattered tens of thousands of years ago, met Comet Encke with its remarkably short orbital period, understood the two streams that composed this extended shower, learned about the 7-year swarm cycle, examined the physics that makes these meteors so distinctive, discovered how to find and observe them, and considered their scientific significance. The next time you see a slow, bright meteor drifting gracefully across the November sky, you will know its story, a fragment of ancient ice and rock completing a journey that began before recorded history. Thank you for joining me tonight on the Nocturnal Astronomer. I hope this has enriched your appreciation of these remarkable meteors. Until next time, keep looking up.